Okay, my name's Matthew Lucky. I'm with CAIDA and I'm going to describe a project that we're currently doing with Internet 2, investigating R&E routing policies in the wild, which is part of a broader project you might have heard Steve talk about that we're calling Root Bear, funded by NSF. So a very brief primer. So R&E networking fills a gap where institutions need to be able to exchange large amounts of scientific data globally, and that's impractical using commercial CDNs. The focus of R&E networking is on connectivity between members, and members may have to arrange their own commodity transit. So in this diagram, we have two R&E ASs, A and B, and B, the network highlighted with the orange arrow, may receive two routes to a commodity route via Lumen and a R&E route via NISANet, with the same AS path length. So which route does ASB choose? To deterministically select the R&E route, we know that ASB has to set a higher local preference on R&E routes than it does on commodity routes. And so we had a question about a year ago, empirically, do R&E networks actually prefer R&E routes over commodity routes? This is a difficult question to answer empirically with BGP data, for example, because BGP hides the information we need to answer it. We don't have visibility into decisions downstream of a view. NISANet can't know that B has assigned a high local preference to it, for instance. And the public view that we have through route views and RIS covers about 1% of the R&E ASs. Atlas gets you about 8%, but then different systems in different parts of an autonomous system can experience different routing policies. So if we want to investigate R&E routing policies at scale, which we do, then we're going to need to do something different. So we're going to need to be able to originate routes whose properties we're going to measure, and then be able to measure the global effects of those route announcements without requiring any of the other ASs in the internet to do anything special to assist the inference. So the approach that we've taken in conjunction with Internet 2 is that we have a measurement system connected to two networks, the R&E network and a commodity network. We announce the same prefix via both R&E and commodity. So the R&E in this is highlighted in green and the commodity is highlighted in red. And so now we see a path to B, showing the path that the routes take. And if we want to know which path B takes back, then we can send it a ping packet and then look at the interface that the response comes back in. So after we send a ping probe, if we get a response via R&E, then B chose the R&E route, otherwise it chose the commodity route. So to get back to the original question about local preference, what we did was the route that we announced, we made changes to over time, prepending changes. So we started with many prepends on the R&E AS path announcement, so that routers that local prefed R&E higher would just always select it and we could be confident that that's what they were doing. And then we increased prepending on the commodity route. So routers that local pref commodity will continue to select the commodity route even when it's long. And then the networks that local pref R&E and commodity equally will switch from commodity to R&E at some point during the experiment. So we investigated this question, and we found that approximately 80% of the prefixes in the global R&E table that we could measure, not all prefixes were responsive, there were 12,000 responsive prefixes, but 80% of the responsive ones followed the R&E path back, always. And at least 75% of the ASs in the R&E table had at least one prefix that did this. That's the other column. There was a smaller percentage that always followed the commodity path, and then another portion that appeared to assign equal local preference to both R&E and commodity. So that was a bit of work that we did with this system that looked at R&E routing policies. And we wrote a research paper that's published and publicly available, and I encourage you to go and take a look at the paper. It has a lot more details than that. With friends at Surf, we also looked at if we had announced the route in Surf, do we see things differently? We basically see the same thing. We look at path prepending policies of routes that are being announced by R&E networks and correlate them with local preference assignments. And then we look at what happens when R&E networks assign equal local preference values. So go and take a look at that paper. But part of the Root Beer project, which is the part that we're now beginning, we consider that what I've just described is a proof of concept. So we built a prototype system to investigate this local preference question, but it was very difficult to operationalize. We needed someone logging into routers, we needed someone logging into systems to send the ping packets and so on. And we also recognise that there are security relevant properties of R&E networking that we want to better understand that we can now investigate now that we've proved that the concept. So now we're building an operational system to support R&E routing policy inferences, hosted by Internet2 and funded by NSF, and this is the focus of the rest of my talk. So because R&E networks generally prefer routes from other R&E networks, announcements into the R&E networking space have high impact in the R&E community. And there are three things that we are going to look at in this talk that we're beginning work on that speak to specific harms. So a member leaking commodity routes into R&E will attract traffic that they might not be prepared for, because now they're going to be the best path for potentially a YouTube. A member leaking R&E routes into commodity can result in traffic across the R&E infrastructure that should be using commodity. And then finally, a member that announces an Anycast prefix into R&E can attract traffic that's best sent to other Anycast instances outside of the R&E ecosystem. And these problems are not theoretical. Steve Wallace at Internet2 has written a number of blog articles that I'm going to highlight. One of them highlighted what happened with 3 impactful routing security incidents in last year, where in one case, commercial routes were leaked into R&E, and what happened was a South American R&E network mistakenly announced commercial internet routes into R&E. And so other R&E networks, because it was now their best path, because they assigned a higher local preference to things they learn in R&E, routed commodity traffic that would otherwise go into commodity through the R&E network into South America, and then it would pop out somewhere else. Another incident where R&E routes were leaked to commercial net providers, an R&E member in the Middle East accidentally leaked R&E routes to its commercial internet provider. Some operators in the R&E space, what they do is announce more specifics in the R&E table so that they can attract most of their traffic through the R&E community if the other R&E partner has that most specific route. But now that the most specific route is appearing in the commodity table as well, the traffic then ends up being routed through, in this case, the Middle East, because it was the most specific route. And as a result, some members have withdrawn more specific R&E routes to minimize risks. So what this speaks to is the need to be able to prevent leaked routes. Steve has written another blog article about this. And the gist of it is that at the moment, Internet 2 requires US R&E networks members to authorize Internet 2 to then announce their prefixes. So it's not enough that they receive a BGP run announcement, they also have to be told that you should expect this and we authorize you to propagate it further. With international R&E pairs, the filtering is lighter, mostly focusing on things with obviously bad things in them like tier 1s and paths where you would not expect bygone routes, etc. So the plan that we're trying to fulfill with the root beer project, with our active probing that I'm going to describe shortly, is to be able to move towards an actively maintained public filter on all pairs. So this will allow the current mutual transit arrangements that are currently in place while preventing leaks, and the list will be public and shareable with other R&E transit networks. And we're going to be building systems support for this. So, instead of just probing R&E advertised prefixes as we've done in the past, we're going to use the same idea and probe all routed prefixes and make some inferences based on the responses. So, we're first going to look at leaking commodity routes into R&E and some initial findings. So, for routes leaked into R&E, what we've done to start with is we've looked at the prefixes that Internet 2 is currently filtering because they're not authorized to accept the route from an R&E partner in the US. So in this case, the prefix ASB is announcing is unexpected. So now we want to know, how is the route coming back to us? We'll send a ping packet to it, and if the reply comes back over commodity, given that we typically expect responses to come back over R&E, then maybe that route has been leaked. So an initial result. So we probed everything, and we found 145 IPv4 prefixes not covered by other authorized routes, that where responses, 54 of those 145 returned over commodity. So that's a rate of 37%, and if you think back to the beginning of the talk, we'd expect maybe 8%. So some of these are commodity routes, you would think. And we see in the AS paths patterns that look like this, where Internet 2 is receiving a route from a US pair with cogent in the path. And the traffic from X is coming back over commodity because they don't in fact have an R&E path. They're connected to cogent, and their route is being leaked. The second one, leaking R&E routes into commodity. So in this case, we've got a route coming that we announce, that is announced to ASB, who in this case is leaking to Z. It's leaking the R&E route back up to our box at the top there to Z over a peering link. And we probe that address that Z is originating, an address in that prefix that Z is originating. And because the path back that Z follows will be via the peering link, even though it has a longer AS path because it's a peering link and will have a high local preference, then we will see the packet come back via R&E. So there's a bunch of inference work that we're doing on this, but we're breaking the results down now for this set of results into two dimensions. Routes that Internet 2 have filtered. So Internet 2 receives a red announcement, so maybe it's legitimate, but it's not been authorized yet, so it's been filtered. And that covers a small number of ASs, a small number of prefixes, and many of these are probably legitimate. There is another set where Internet 2 is not receiving a route announcement, and these perhaps are more suspicious, but we break these down into the networks that are originating other R&E paths, because they probably also mean to announce these prefixes as well, and ASs that do not originate other R&E prefixes. And those are the ones that are probably the most suspicious in that they're receiving leaked routes. And there's 94 ASs that appear to be receiving leaked routes, 164 prefixes in the global internet table. And then finally, we're just going to close with members leaking Anycast routes into R&E, because they're going to be attracting traffic best directed to other Anycast instances. And this has been hard for a while, but recently there are daily Anycast instances provided by the University of Twente using CAIDA infrastructure to build these censuses publicly available. And so there are about 13,000/24 Anycast prefixes, and we probed all of them from about 260 different ARC vantage points, CAIDA ARC vantage points, the measurement infrastructure that CAIDA operates around the world. And these systems are in a mix of R&E and commodity networks, and we focused on the 70 Anycast prefixes that are also in the R&E routing table provided by Internet2 to route views. So I'll begin with one what this graph shows is we're breaking things down by R&E, the green line, and commodity, the red line. And this is a CDF graph. Basically, the way that you interpret this is the green line being on the left is good, and the red line being on the right-hand side of the green line is bad because they're having a poorer RTT. So in this case, the iRoute DNS server is in Internet2's routing table, and for the US at least, we're only focusing on the US nodes in this graph, but if these routes are being accepted in Europe, and Europe are following them, then they're going to see something quite a bit different, like the next graph I'm going to show you, where the R&E path is good, 40 milliseconds, the median compared to 60 milliseconds for commodity. But now we have an example of a case that's not so great. Some APNIC DNS servers, Anycast, there's an instance on the US East Coast, but R&E is seeing a path to Sydney because the green line being over 150 milliseconds for most of them indicates the packets are going to Sydney, and also the AS path says they're going via RNet. So this is in terms of what to do. It's been difficult for networks around the world to identify, in fact, which prefixes are Anycast because there's no community, there's no tag on them. But we have a census now, and it would be useful to go and revisit the export policies for Anycast routes and maybe limit their propagation outside of a geographical region where that makes sense to do. So in summary, R&E routing is unique because R&E networks generally assign higher local preference, and R&E networks provide mutual transit. We're going to be building a set of operational tools to help with finding and diagnosing these problems and preventing them manifesting further. We've developed and deployed a ROA planning tool already, and we're shortly going to be delivering tools to assist in inferring and improving R&E routing policies based on the things that I've just outlined in this talk. Happy to take some questions.
Any questions for Matthew?
I have root beer barrel candies to hand out in honor of root beer. So if anybody wants one, come see. I was going to throw them, except I was warned that's probably a bad idea. So.
When has that ever stopped you?
That is true. All right, ready, Jeff? A whole bag.
All good?
All right,
Thank you.